what's going to happen to the distribution if I do nothing? Assumption, right? The assumption, the generalized assumption, is that the mean and variation, right? Mean and relative systematic variance, let's call it here the sigma squared variance, right? Is going to sort of stay in its lane. It's going to do its thing, right? It's not going to change heavily. Now, just the selection bias can occur, right? We're not going to see a big shift here. And that is to be expected, right? That's what we should expect, is that nothing changes. This is the control factor. We didn't do anything, and so we shouldn't see any differences. However, if we do something, we talked about, I love to talk about these little acai berry or whatever, you know, like the superfruit things. Like you get them, they're pop-up ads on, you know, some website, and you look at it and it says, you know, eat this fruit once a day, or drink this cup of something, and you'll lose millions of pounds, you know? It's like, or you'll literally turn into a black hole and suck the environment around you. That's how much weight you'll lose. So, we have the same distribution characteristics, right? This is our original distribution. But what's happened to the original distribution is some changes have occurred, right? So we have the, let's go ahead and call this is the original distribution. That's the dotted line. And we did something, okay? Something happened as a result of this circumstance. And what happened actually caused a shift in the mean of that distribution, right? So I have the original baseline, and now I have some delta, right? This one says, this is the original, right? And then this is the consequence, almost exactly the same. This one says, this is the original, and this is the consequence. Now, what would happen here if I looked at this from a plotting perspective? Let's look at this, plot this in two directions. Here we see weight of the user as a result of the time that has passed with regard to the experiment, right? We're going to have two projections here. So this is time t. And the first one is that we have a weight characteristic for the original group. This is our control group. What happened to the weight over time? Nothing, or very little, okay? What we're actually looking at here when we look at this, from this perspective, when we look at this system, the distribution is here, right? It is how wide of an area the values are spread out for, right? So there's going to be a range over which every individual in this group has a slightly different weight, right? So we're not going to have a perfect, you know, every single individual is going to maintain exactly the same weight. So we wait 6 months and we weigh everybody again. Well, some people will have lost weight naturally, some people will have gained weight naturally, or there may be sort of a generalized trend toward weight gain. But what we note is that there doesn't seem to be a large deviation between the original assumption and the subsequent measurement. Right? The average at the beginning of the system and the average at the end of the system are likely almost identical. In this particular case, I'm going to draw this one as the black line target. We're going to say that over time the system started to deviate from the expectations. The idea of rejecting the null hypothesis is the satisfaction of the absolute value of the t-test, initially indicating that what is the impact of a linear or curvature element on this first element, right? This is the null state, and then this is the H1 or HA state, right? So this is H1, hypothesis 1. Null hypothesis would say that the values encountered at some time t, so delta for H values at t is correlated to or directly related to only the mean or the expected value of the distribution characteristic, the weight. But if this is not true, right, so this would be null. If that one is not true, known to be not true, because of the fact that we see a difference, right? So if I pick some time t, and I choose to look at some time t delta in the future, right? T plus n, and I go up and I sample the system. I'm going to get one distribution here, and then the other distribution here. These reflect a perspective on the original distributions. If there's a difference between them, right, we note that values should fall within a certain range along the road of this system, and values should fall within a certain range along the road of this system. If the width of those roads is different, then we have the ability to conclude that there is something significant about the changes in the underlying system. So we could say that there exists some function. We have done these in the past. We said H1's hypothesis implies that there exists some function F1 that is now impacting weight or taking t and causing a change in weight, right? With respect to the presence of a value. Now we say in this case, null hypothesis implies that the function, so what does this function contain? This function, right, f of x, is, we would say, is equal to y, right, y, which is the weight. So we say y is equal to our beta 1 times the time coefficient characteristic plus our beta naught, which is our interface coefficient, right? This is the mean of this distribution. If there is no correlation, then it'll just be that at some time t, the bias will just be the bias. It will not have changed. But if the bias has to change, that means the mean of the distribution has changed, right? So if I have to change the offset in order to compensate for some adjustment at some future position of the feature of interest in order to establish a regression, and that value has deviated more, right? So if this one here had this space, and let's say that this one here is over on this side, right? We say that this space, if this deviates more than that 5%, that it is considered statistically significant. What you did changed something. You go to the doctor, and they put you on the treadmill and make you run, and they check your heart rate and breathing and all that stuff, and they go, yeah, you're gonna die. You're like, I knew that, doc, I just wanted to know when. I was like, it could be now, it could be tomorrow. No, what they do is they say your chances of heart attack, heart disease, whatever, they're up, they're elevated, right? You're overweight, you don't exercise enough, your diet's garbage, all you eat is saturated fat. You're done. You're on the downhill slope, right? The survival of everybody on a long enough timeline reaches 0. So when we think about it, we say, here's your current likelihood, right? You have a current likelihood of survival. It's kind of this little timeline here. And we say that your likelihood of survival is going down over time, okay? What we would like to do is we would like to imagine some branch that comes off this system that adjusts that perspective to slightly elongate that spectrum, that possibility. The spread spectrum here is you did something new, right? You changed some pattern of behavior, and as a result, you created a delta in between your expectations of the original state, unchanged, and the expectations of the new state with an intervention. I say, how do I know when an intervention is scientifically established? when the new values fall outside of an overlapping confidence interval to the perspective where we're more likely to see the new samples around the new mean than we are to see the samples around the old mean. In some senses, this is simple. But in other senses, we're thinking about it in terms of, we've got a lot of moving parts, right? We have two separate experiments we're running now. We're running one where we're collecting data from one group of people, and another where we're collecting data from another group of people. And in that respect, what are we dealing with? Well, we're dealing with having to keep those two things separate and characterize them separately. Each of those is going to get a model. We're going to have a model for the original hypothesis, and we're going to have a model for each of the subsequent hypotheses in order to determine whether or not what we're doing has efficacy in implementing a reliable solution. Okay, everybody good with this? This does matter a lot with pretty much all scientific disciplines in general. This is kind of a natural extension of the scientific process. I have to have some metric by which I can determine whether or not what I'm doing has the effect that I'm looking for. And especially if it's an experiment that I'm looking to try to really establish, like without a doubt, you know, when it goes past that initial hypothesis where you do the experiment once, and then you do the experiment 1,000 times, and you see whether or not it genuinely has an outcome that is consistent, that's where we're talking about, is how do we characterize that with respect to small variances in the process. One person could eat 10 pounds of side berries a day and never lose any weight. Right? The other person can take a little supplement pill and all of a sudden, you know, they're supermodel skinny, right? That's a situation where different things affect different people. But if we want to try to make an inference to you that it's a generalized concept, we talked about in those first couple of slides, we had heart disease characteristics, right? I said, you stop smoking 3 cigars, you know, a day, and, you know, drinking, you know, your big gulp of cognac at night, and, you know, like stop eating like every meal of the day, 3 pounds of red meat. Like maybe, you know, just maybe you won't die of a heart attack next week. The idea is we had people that did that, right? They changed that behavior, and then they didn't die as fast as the people that didn't change the behavior, right? So now I actually have something to base my perceived conjecture on. But what have I done here? I've created an empirical process for assessing the quality of 2 different models. One in which you keep living your life as it was, and then the other in which you do something that I have suggested as a specific set of adjustments. Those are H null and H1, right? So if I reject the null hypothesis, that would be a consideration where most of the people that do what's suggested live in a degree longer than what was anticipated. So I say, what's significant at that point in time? Well, they live at least 5% longer. Here's the question. So if you're going to live at least 5% longer, is it worth it to you to live 5% longer, right? You always have to ask yourself that question, right? What am I getting out of what I'm doing worth what I'm looking for here, okay? So let's look at a couple of things as they break down. We say p-value degrades below 0.05, okay? So 5% is the minimum sub-requirement for deviation in significance. Anything that is below that value, right, means that there's less and less overlap, or less and less likelihood of an overlap between the null hypothesis and the HA or H1 hypothesis. So the higher the deviation between these, the lower the p-stat goes. Why is that? Because this ratio here will do what? As the standard error between each group, delta, offsets, the standard error gets higher between each group. So that makes the beta hypothesis, which is the slope characteristic, is going to be divided by a larger and larger value of the standard error as a result of the 2 models. So if I try the same slope on 2 different sets of distributions, if I try to keep the same slope and I say, what happens to the standard error? As those distributions deviate, it will maintain being good for one, but the other one will get worse. So what happens to the t-statistic in the system? If I say delta of H naught and delta H1, H1 is where I keep changing it to attempt to adjust for those new considerations, and H naught is the original consideration. So the value of the t-statistic, the absolute value of the t-statistic, as observed here, is that as the standard error increases, that t-statistic gets smaller and smaller. So we say that they are statistically separable by the fact that this model will work on one set of data, but not on the other set. What does this actually look like to us? Honestly, it looks a little like overfitting, right? Because it's deviation in the quality of fit for the data. But one of them says there is actually no regression, there is no coefficient, there's no correlation. So as soon as there starts to become correlation between the elements, as soon as there is a functional difference between the elements, we will see a falling off, a continual falling off in the separability between the two systems, right? So here we see the intercept between the multiple elements of the system of those three values that we previously interfaced, the TV, newspaper, and radio. We see the standard coefficient here for the intercept, and then we see the regression coefficient for the valuation, and then we see the standard error as a result of the regression coefficient. So what is that? TV's regression coefficient has a value of 0.04. That's a slope of 0.04. That's tiny, right? It seems relatively uncorrelated, but it's not zero, okay? And it is not zero in a way that if I was to compare it to zero for that factor and what the requirement for the intercept would be, essentially with a zero characteristic, right? Intercept is TV without slope, right? Null hypothesis. What does the coefficient have to be for the null? This is beta naught. So beta naught has to be 7 here. The standard error generated by that system is 0.45. The standard error generated by a 0.04 beta 1 coefficient for TV reduces the standard error to 0.0027, right? Well over, what is that, 8 orders of magnitude? Yeah, well over 8 orders of magnitude, okay? Notice what happens to the t-statistic there. The base t-statistic stays the same, roughly, but the p-value is correlated how? The delta between the two, right? So the difference between the base t-statistic is going to be a nominal value below 5%, or below the 0.05 for the p-statistic. So just keep in mind our core consideration is p-value says how significant the difference was as a result of the standard error here. Yes?
How we are getting the p-value? Can you explain it again?
So we say that values for t delta, right? So that is the absolute value of t is going to be, you're changing t-statistic, you're looking at the difference in t-statistic over the relationship in standard error. I'll find the equation for you. It's big and it's crap, so just don't worry about it. It's not worthwhile. It's not what we're actually here for.
Okay.
We're here because we can utilize this. We can utilize this confidence interval,
Okay.
right? Standard error here. So we look and say beta 1 minus 2 times SE, right? So what's the standard error in this other case? Look at the magnitude of the standard error. If you take 2 times the top value, that's a big number. You take 2 times the bottom value, it's still tiny, right? So the delta between those two, the ratio divided by that characteristic of the t-statistic is going to give you your p-value.
2 times of the standard error.
2 times the standard error. You take double magnitude of standard error. Because standard error goes in each direction on either side of the value, right? You have the positive aspect of the standard error and negative aspect of the standard error. We have one window here in which things can occur. We have a subsequent window here in which things can occur. We have the difference, the delta between those two, relative to the values of the standard error of the system. They become statistically separable when the rate of change in that p-value is less than that 5% of the error that is outside of the confidence interval of the previous assertion. Is that more clear?
Yeah.
Okay. I don't really want to get heavy into this. I was wanting to describe it from a theoretical, conceptual level. The mathematics of it are more, they're more like raw stats level. And like I said, if you really are into it, fine, I will get it for you. I can give you a handout for it. We can look at it. But I'm more interested in what we do with this, okay? How we use this in the future is the concept of how we compare multiple different types of regressions and determine their quality. Okay, so if I can make the assumption that as a result of some effect in the world, the regression changes, then I can say that there are a series of possible models or possible mechanisms by which I can use the residual standard error to calculate the best or most likely value for an individual distribution. So what do we see here over on the right-hand side? At the very bottom, we see RSS, right? Residual sum of squares. We've seen this one before. This is just the condensed version of this guy, right? Residual sum of squared error here says that all of the points, localized error of all the points is associated with each position times the hypothesis value for the assumption, right? And says that all I have to do in order to determine the total summation of error for the system is calculate all values of y minus y hat for the values that are given, right? But I want to understand that with respect to the idea of RSS, right? So I say RSS here. RSE is related to RSS by this process. It says RSS is just the total error, right? I added together all the error in the system. But I didn't take into consideration anything related to the quantity of samples in that consideration. Now, previously when we did localized regression, we calculated it relative to the quantity of samples. We spread the blame around. So one of the big points here is we need to go ahead and figure out a way to attempt to minimize the error for local regions without allowing singular samples with very high error offsets to pull us off the norm. How does that relate to what we were talking about with the standard error? Well, if you have one sample that is very far away from the line, that particular sample is going to contribute heavily to the doubt that you have relative to your confidence interval, right? If it's a sample that's far outside of the range of interest, how do I balance trying to make sure that all the samples within the data set are satisfied without getting into a situation where I'm summationally taking larger values with the total summation? I want to try to say that I want to reduce the value for the largest number of samples to the lowest value. By doing so, I take the square of the absolute magnitude, or the absolute magnitude of the error, and I divide it by this value of n minus 2. This is the number of samples in the series minus the n points, right? The first sample and the last sample. Now, keep in mind, this slide is a little bad, the way it's written. It almost looks like it says RSS equals this thing over here, right? Because that RSS is real, or the equals is close to that little RSS. That is the whole thing, right? The whole thing. RSE is equal to this. Matt, cover this up for a second and say this is RSE, right? this one here expands into this. So that's two separate, it's two separate equations. It's not breaking out RSS into a separate item. It's expanding the definition of RSS down here into this equation for residual standard error. Now what happened when I did this? I just turned it into an iterative formula. Now what happens whenever I build things on this iterative formula? What do they look like in terms of calculation? I just calculate the value at each individual point and aggregate it all together, and I'm going to get a singular value, right? So there's one singular residual standard error for all the points in the regression. We talk about this with respect to another calculation that is part of something that we're going to calculate that is slightly more potent for us than p-value. Okay, that's the reason why I say p-value doesn't matter a whole lot. P-value matters in like computational statistics, but we're going to use our own version of it, or a smaller version of it, because p-value works for one intervention, right? One thing at a time. We want to be able to do this for multiple things at a time. We want to be able to do multidimensional analysis. We want to do multilinear regressions, right? We want to take more than one thing to one thing. So I say that R squared is a metric we utilize, and it is just called R squared, okay? I don't really know why this is boring, but it's just big R with a square on it. It said it is a fraction of variance that is explained. Let's talk about that. What is explained variance? Well, okay.
Something that you can correlate to a change.
You're very close, very close. That's nice. That's a good thing, right? So I say variation. There's two data sets, right? That's what we talked about beforehand. We said variance of the data sets. If I have a model that explains the correlation between those, or explains the difference between those, right? Then I have a ratio of which I can say why, or to what degree, the change in the system was affected the model itself. So model hypothesis A and hypothesis B, right? If the slope changes between those two, then I would say that, for instance, let me try this. If I have performance, so I have training performance, right, and testing performance. And I was to look at this and saying hypothesis 1, and I said training performance was something like 70%. And testing performance was something like 68%. Okay? And then I have another hypothesis that says 73%, but only 66% performance for testing. Now we have an increase here. This is higher, but this one's lower. What have I guaranteed that the changes are going to be valid in those circumstances? Each one of these is a separate model, right? So between training and testing, I see a delta that's caused by that system. Let's add a third one in here and see if this helps. H3, this one is 78, and this one is 72. Notice, that final model is actually outperforming either of the two previous models. For H2, we might assume that that model was overfitting, right? For H1, we probably actually assume it's slightly underfitting, because now we have the ability to compare to performance. In the final case, we adjusted some stuff. So we know what this is. This breaks down into some factor of beta 1 and some factor of beta naught, right? So we adjusted these. How much, right, by how much did I change each? And how much did the amount that those things change correlate to those changes in output in performance? When I'm talking about it in terms of R squared, I'm talking about it in terms of the quality of what we call the true sum of squares, right? So the true sum of squares is down here at the bottom. It's just essentially the same thing as RSS, but it's called the total sum of squares because I changed from my assumption to what? The mean of the distribution. So the true or total sum of squares is related to the mean of the distribution. The residual sum of squares is related to the individual value, the individual aggregate value, and the residual square error in this case is related to the number of samples, the square root of the number of samples minus 2, right? So over this number of samples minus 2. In this case, we would say R squared is this true sum of squares, right? The value relative to the mean of the output minus the value of the assumpted value over this value, right? Is the delta, is the difference between the two. Or rewritten, you can say 1 minus RSS over TSS. So TSS goes on the bottom, that is the mean characteristic. So it's how far away the sample hypothesis is deviated from the mean. And at the beginning, it is the variant characteristics between the two samples. So we have the variance for data set to data set over the variance in the expected mean of the target. This one is correlated to a calculation which we utilize in linear regression called correlation, right? So R is correlation. This is also called the correlation coefficient. So this one starts to get a little nasty, but ultimately, if you look at it, it looks familiar, right? Does it look familiar to anybody?
Which one?
This R value here, right? So we say that R squared, this R squared, 1 minus RSS over TSS, is related to the R squared for correlation, right? Where if I took the square root of this whole value, I would actually end up setting this equal to that RSS over TSS.
Looks like beta 1.
It does. It looks almost identical to beta 1. But what's the biggest difference? Oops, I passed it.
The denominator.
The denominator, right?
Yes.
So we still have the characteristics of the deviation. So this is sum of deviation. This is sum of how much, sum of the product of the deviation, I guess you could say, of deviation in both x and y. But what am I doing on the bottom here?
You're multiplying it by TSS.
Exactly. I'm getting rid of the total magnitude of the error characteristic, right? So the top section, magnitude is, it is signed, right? It is a signed direction characteristic, but eliminated by product. And the bottom, I'm squaring the offset between the value and then taking the square roots before multiplying those characteristics with one another, right? So it is, the first characteristic is the beta 1 coefficient over essentially the total sum of squares calculation. What we're saying here is that the closer this fits, so let's look over here at this side of it. One, if the ratio of the residual sum of squares for each individual point over the true sum of squares, what happens as the residual sum of squares gets smaller? True sum of squares is not going to change because it's calculated based upon the mean. But the residual sum of squares will change because that's where our model is. That's where our hypothesis is preference. So, what am I talking about here? If this doesn't change, because that's the mean characteristic, this doesn't change because it's the mean characteristic, right? That's the null characteristic. That is assuming that the error is relevant, or the true sum of squares is relevant to the distribution of the mean characteristic, right? Just the biasing terminology. I then introduce my model up at the top as the RSS, residual sum of squares. that becomes my HA hypothesis. I see a deviation between these two things, and I take the ratio of them, and I end up with the R square value. The quality of how well the model fits will be related to that RSS over TSS. What ends up happening here? So if this is, the RSS is my model, and TSS is essentially my null hypothesis, I have the model, right, beta 1, standard error as a result of beta 1, this categorization here will converge to 0, right? So this will become 1 if the model is absolutely not describing anything useful. And will become, the RSS over TSS will become 0 if the model has perfectly captured all the variance. So a perfect R square function, meaning the model that is the best or is perfect at describing the system, will be a 1. And the model which has no correlation between the two systems is a 0. Why do I call it the correlation coefficient then? Because it's simply, if you take, it is simply the relationship between the magnitude of the error and the individual characteristics of the samples that are entered into the system. So the R square value provides us with an improvement in overall performance relative to both the deviations in the means of the sampling and the deviations between models relative to the considerations. So one assumes null and the other one assumes my model. If my model is doing better, model to model, what's going to happen to the R squared? This becomes a whole value. R squared becomes a whole value that I can use to compare the quality of the model to model, in a apples to apples way. By eliminating the variance as a result of data set characteristics for the mean sampling, and then eliminating the variance characteristics for individual samples as a result of the residual sum of square error, I have now eliminated all of the things that make one data set different than another data set. Right? We said, how do I compare a regression model for this data set to a regression model for this data set? They have different means, different standard deviations. They have different qualities as a result of the total sum of error. Once we take the magnitude characteristics of the error out and reproject it as a ratio, now I can say how well your model is performing relative to how diverse your data set is, versus how well your model is performing relative to how diverse your data set is. Right? If you have a really well-positioned data set and your model is doing just okay, and you have a really bad data set but your model is doing excellent, I would like to be able to tell you that you're doing excellent and you're doing just okay. How can I do that if I'm not on an apples-to-apples basis? How can I do that if I haven't removed all of the deviation characteristics that make data set to data set variation inconsistent? That is what this equation does. It eliminates all of the other variance characteristics that make one set of deviations different than another. Guess what then? We're all comparing them all relative to the same distributional characteristics. And as a result, I can take one model and say that it is performing equivalent to this level on this data set relative to the amount of total internal variance and noising characteristics and irreducible aspects that are present. Now, why would this be useful? If I have a different metric for every single model relative to the data set that it's performing on, I don't learn anything when I do a model, right? I don't figure out how to go forward in the process of the next system. If everything is just unrelated and unlinked, then I can't figure out how to make a model better.
So it's relating all the models.
Like I said, this brings everything onto the same page.
Same page, okay.
Same page. All models can be reprojected into this space. And the cool thing about this space is it's a bit like a probability space. How's it like probability space? It's a ratio relative to the total probability, right? What's the perfect fit of the model? That's a 100% model, right? 100% perfect performance. That's a 1. What's a model that does absolutely nothing? That's indeterminate. That's a H naught hypothesis model. That's a 0. So it is the range of likelihood of this particular model to fit to this specific data set. So the likelihood of the fit is going to increase up to a value of 1. So we say, if you ever see R squared in a regression fit at the bottom, it'll usually be like a 0.92 or a 0.78 or something like that. We could say that it is a 78% fit to the underlying variance characteristics of the data set in that particular model space, right? So model to model, data set to data set, comparing the apples to apples between training and testing, comparing apples to apples between multiple different models for different data sets. By comparing their R-square value, I can say how well they're doing at capturing what we talked about up here previously, right? We said previously that there was a, what did I say? Yeah, fraction of the variance explained, right? So we have variance, and then we have an explanation of the variance. So the better the variance is explained, the better the model fits to that very characteristic, the more or the better the improvement is in total performance. All right. For average performance in advertising data, we have residual standard error of approximately 3.2, an R squared of 61, right? So this is roughly a 61% score performance. And then an F-stat, which we haven't really talked about a lot of F-stats, but F-stats show us a receiver curve of 312, okay? How do we get there whenever we have multiple factors? So one method is to interpret the value for beta J in some system based upon the average effect 2y for 1 unit increase of x of j in the previous setup of the system. What am I talking about here? Remember our core goal of this is to do multivariate. How many factors of x am I bringing in here?
3.
X has p dimensions in the equation up above, right? What was p?
2.
This is something I expect everyone to know. This will be a question for you, yes.
3. It's
Okay,
related
correct.
to each
P in this particular case would be 3 because
we're doing TV, radio, and newspaper.
correct, there
radio
are
and
3
television.
features in
3
this
features.
system,
3 features.
Okay, so we count from 0. So this would go all the way up to x of 3, right? So x of 0 is what? There is no x of 0.
1.
X of 0 is the bias.
Bias.
Okay, so we have x of 0 that's related to the x, the bar of the system, right? So beta 1 times x1 is the coefficient, the regression coefficient for TV. Beta 2 is for radio, and beta 3 is for newspaper. Okay, how can I just put these all together in one big equation whenever I have 3 separate regressions I have to deal with? Well, I want to try to understand why, as a relationship of money being spent on all 3 of these advertising sources. I don't want to just advertise exclusively on TV. I don't want to just advertise exclusively on radio or podcasts or whatever, right? I want to advertise on all 3 of those sources, and I want to see how changing the values that I'm putting together, investing in each of those, affects the ultimate output, which is the sales goal. So now that I have the tools that I need, I can figure out how to minimize this system in multiple dimensions simultaneously as a result of the comparison of the residual sum of squared error for each of these beta coefficients to the remainder of the beta coefficients, looking at it as if I were to be looking at the value of beta average on y, right? So beta j's average effect on y, what is that? That would be our residual sum of square error, right?
Yeah.
So our RSE is the average that some specific beta has on the output target. If I hold all the other values static, right, and I just adjust the amount that I'm spending on TV advertisement, I would see a proportional increase or decrease in Y over there. And as I keep holding each one static, I keep moving the others around, and I look at the aggregate of performance for the total value of Y. And I'm actually going to end up having a correlation coefficient characterized relative to each of these betas to determine how well it's doing at modeling its own individual data relative to this residual sum of error, right? Plus, I'm actually going to have a total assessment of the proportions of the operation for the entirety of that model from a combined perspective. One of the biggest problems we have with this is, well, we'll talk about it later on. I want you guys to think about what some of the problems with this might be. Okay? That's your take-home assignment for Friday, is I want you to think about this. You can skip forward in the slides and sheet if you want, but I would actually prefer you to actually think about it because I think it's better. Tell me why this might be problematic. Why this approach of just holding all other elements of xj, all other predictors fixed, while doing the predictions for the local value of the regression. Okay? We'll talk about that whenever we come back, and I'll see you guys on Friday. I'm going to put out the lab for chapter 3, which is the linear regression lab. And you guys will have about, I believe, almost 2 weeks to do that one. So, because we're not going to be finished with this until next week. And then when we get to classification, we'll start on the classification one. So, just note it, it's not going to be, not forever, and it's not really a lot harder than what you've already done. You just are going to actually be using some models to do the regressions and plotting the values of the regressions for this coming chapter.
So
it's
just
more
kind of
exciting.
follow
Get to do
the
something
lab
fun.
again?
Yeah, they're the same. They're the
Okay.
same. All the labs will be the same. It's just following a set of instructions. Really easy to walk through it. And then what you'll do when you get done with that is you'll create your own version of it. You'll go to a new data set and you'll do the steps on your own data set.
Okay, and we get to pick from that list of data sets that we want to do it to?
Correct. We're
Okay.
going to use that same data set. We actually, I might introduce a couple more for you to select from if you're interested.
Okay,
I have some that I added at the end as the final project data sets. And I've been thinking about integrating those earlier on in the semester, so I might put those up available for you as well.
okay.
So,
Thank you.
sure.